Okay, so hello everyone. So welcome to the 10th class on statistical mechanics. This is a part of my PMRF TA-ship that we're doing. I'm Sauravi. I'm doing my PhD here at IISc Bangalore. And in this course, till now, we have been discussing about, so we started with thermodynamics, then we went to uh, statistical mechanics, where we first looked into different ensembles, okay, and that's the probabilistic approach, and it was the classical way of looking at it. And then we gradually moved towards the matrix formulation, where we spoke about density matrix, and then how for any density matrix or any matrix, the elements depend on what kind of basis you choose, so how you can go from one basis to another, and how does the density matrix differ when you have a pure state or a mixed state? What do you mean by pure state or mixed states, right? And then all the different ensembles that we had initially discussed uh, using the classical formulation, we also tried to do it in terms of matrices, right? And then we moved towards quantum statistics, where we saw that now based on how the particles are. So you describe the particles by some wave functions, and based on whether the particles are described by a symmetric wave function or an antisymmetric wave function, you can have different kinds of or different ways of distributing these particles into different energy states. And based on how they get distributed, so that defines the different thermodynamic variables or the relations that relate the the microscopic picture to the macroscopic thermodynamic variables like pressure or temperature, all of that. Okay, so in the last class we talked about we started with the general quantum statistics, where we looked at we tried to differentiate between distinguishable and indistinguishable particles, and how the distribution varies as you go from classical particles to quantum particles. So we did discuss about all of that, and okay, and then we spent quite some time talking about Fermi-Dirac distribution, where we looked into how fermions get distributed into different energy levels, and where does this restriction come in? How does this restriction come in? That if you have an energy state, you can have either one fermion or no fermion in a single particle energy state, single particle state, right? So from where does this, so how the fact that fermions are described by antisymmetric wave functions is associated with this mean occupation number, or the fact that how the fermions get distributed into different single particle states. And then once you have this distribution, how you write the different, equation of states, or how you find an expression for pressure, or, temperature and all of that. So we discussed all that in the last class. Today we'll spend quite some time talking about the another kind of indistinguishable particles, which are described by symmetric wave functions, and they are bosons. They have integral spins, and we'll try to see that what happens with the bosons, how they get distributed, and how we can use their this distribution, the number distribution, how that comes in when we try to write an expression for the different thermodynamic variables. Okay, so as we normally do, we'll discuss the basic concepts, how the different important relations or formulae come up. We'll talk about that, and then we'll try to solve some questions. And if there's any doubt, feel free to ask me or get back to me later. Okay, so we'll do a quick recap, because first we'll try to see the common formulation. So we started with the common formulation, and then we focused on to Fermi-Dirac distribution. So today we'll first do a quick recap of the common formulation, where we talk about distinguishable and indistinguishable particles and how this distribution happens. Okay, and then we would move in details towards the Bose-Einstein distribution. So consider an ideal gas in a quantum mechanical canonical ensemble. Okay, so we know that now if you're talking about a quantum mechanical ensemble, then you would have different, quantized energy levels, and they can have different degeneracies as well. And it's an ideal gas, so you should remember that there is no, interparticle or intermolecule interaction in ideal gas. Okay, so in this case, in a canonical ensemble, we know that the typical definition of partition function is given as you see here, right? So Qn, which is the partition function for canonical ensemble, is given as summation over e to the power minus beta e, where beta is 1 by kt. Okay. And now if you say that there are different single particle energy levels given as epsilon, and in each energy level you have n epsilon number of particles, then the total energy is given as summation over epsilon, n epsilon into epsilon, right? And then there is another condition that the total number of particles is given as capital N. So summation over epsilon and epsilon should give you N. So these are the two conditions that need to be satisfied. And this is your expression for the canonical partition function. Okay. So now what you can do is basically you can include this, degeneracy in or the number distribution as following. So you can say that you can write E, the total energy, as summation over epsilon n epsilon into epsilon. Okay. And then here in see, this is summation over all the different energies, right? So here you can include the summation over different distributions. Okay. So how you can distribute your, the particles into different energy levels. So G here is the statistical weight factor, which is appropriate to a certain distribution set, which is given as n epsilon. Okay. And then you do a summation over all such possible distribution sets. Okay. So this is something we have discussed in the last class quite in detail, that when we talk about, classical particles, okay, so these are classical particles, meaning we're talking about distinguishable particles. And there the weight factor is given as summation over epsilon 1 by n epsilon factorial. Okay. And here you have already considered the fact that the particles are inherently identical, but still they are distinguishable. Okay. So that's the classical particle, or you can say the Maxwell-Boltzmann particle. But then there are indistinguishable particles, okay, like the Fermi-Dirac or the Bose-Einstein distributions, as you can see. So in this case, you're talking about indistinguishable particle, where the numbering of the particles do not matter. Okay, only how many particles in how many energies or in what energy state, this number matters. But whether you have the fifth particle or the seventh particle, or if you interchange the particles, those things do not change the microstate that you're talking about. So for that, for such indistinguishable particle, the statistical weight factor comes out to be 1. So for Bose-Einstein case, it's always 1. For Fermi-Dirac case, because there is a limit, so n epsilon can be either 0 or 1, right? So here, when n epsilon is 0 or 1, then you have this weight factor as 1. Otherwise, it's 0. So this is something which we have already discussed in the last class, right? So that means this distribution now comes in the calculation of the partition function using this relation. Okay. So statistical weight factor in like when we started discussing about it in the last class, it was denoted by WNI. So this GNE is n epsilon is same as WNI that we had initially discussed. Okay. And this is not degeneracy that we're talking about. It's the statistical weight factor, which talks about how many ways can you achieve a particular distribution set. Okay. It's that weight factor. It's not the degeneracy as per se. Okay. So then we know that from our understanding of the grand canonical ensemble, the grand canonical partition function would have a relation with the canonical partition function with an additional extra term which comes in because of the fugacity. Okay. And here the only difference between Bose-Einstein and Fermi-Dirac case comes in the value of Ni. What is Ni? Ni is the number of particles that you can put in a given state. Okay. That can be present in a given single particle state. Okay. Weight factor is 1 for both the cases. So now what you can write is, this is your grand canonical partition function. Okay. And you're writing it as summation over n equal to 0 to infinity. This is your fugacity. So z to the power n. And then you have summation over the different distribution sets, e to the power minus beta total energy. Okay. E. which is again written as summation over epsilon n epsilon into epsilon. Okay. Now here, so basically this is your, this part is your, so if I have to write it or point it out, this is your canonical partition function. Okay. And then you have this z coming in, which is because of the fact that now in a grand canonical ensemble you can interchange the number of particles. So for each capital N, you would have a term like this, and then you would do a summation over all possible values of N. Okay, so that's why you have two summations involved. This is your basic understanding of grand canonical partition function. Okay, now here this talks about how the particles get distributed into different energy levels. So for Bose-Einstein case, you can have as many number of particles in a particular state as you want. But for Fermi-Dirac case, this has a limit. So you can have either 0 or 1, right? So now what you can do is, you can just rearrange these terms a little bit. So this gives you these two summations, okay? And this is a product of all these terms. Now this can be further rewritten, okay? How? So here what you have been doing is you have, so as per this two summation, description, what you do basically is you fix a capital N, and then you say that for this particular N, what are the different distributions possible? You sum over all of them, and then now you also relax the fact that your N can also change. Okay, so then you do a summation over all the different values of N. Now this is same as, rewriting it, where you consider that all this possible N epsilon can take as one. So you can now have as many number of, possible values of N epsilons, okay, independent of one another. So what you can therefore write is something like this. So this is same as doing these two summations, okay. So now you are doing summation over all possible values of N epsilon, okay, and then you have multiple such products. So you can write it as summation over N epsilon Z. So this is your first term, then you have second. So here, this, N0, N1, the values that it can take depends on what kind of particle we are talking about, right? And then you can have many such, products. So in the Bose-Einstein case, what happens? Your N epsilon, like N0, N1, N2, all of them, they can take 0, 1, 2, whatever value, okay? While for the Fermi-Dirac case, they can take only 0 and 1. So we did solve for the Fermi-Dirac case in the last class, where we looked into the case where each of these values, so N0, then N1. So when you are doing a summation, you do a summation over 0 and 1. You do a summation over 0 and 1, and then you would have multiple such products. So this is something which we had done in the last class. Today, what we'll be doing is the Bose-Einstein case, where now N0 can take all possible values, 0, 1, 2, 3, 4, right? Again, N1 can take all possible values. Similarly, N2 can take. So that's the change that would happen now, okay? So when you do that change, what you get is two different expressions, okay? So this is your expression for the Bose-Einstein case, and this is your expression for the Fermi-Dirac case. So for the Bose-Einstein case, as you can understand, for this to be defined, okay, so if you just look at this term here, okay, for this to be defined, your, this term here, Z to the power minus beta E should be less than 1. Okay, otherwise it would have no meaning, because here what you are looking at, this term here is the mean occupation number. It talks about how the numbers get, distributed into different energy states. So that being negative doesn't make any sense, right? So this tells you that for this to be defined, Z to the power minus beta E, this term should be less than 1. Okay. And then for the Fermi-Dirac case, you have this expression. So in the last class, we started with, this form, and then we went ahead. So if this is your expression of the grand canonical partition function, how do you proceed? That's something we have done. Today, we will be working with this expression. Okay. So now once you have Q, which is your grand canonical partition function, you can write the Q potential, which is, so this is something which we have, derived and discussed when we talked about the grand canonical partition function, grand canonical ensemble, okay, in previous classes. So Q can be used to define all different thermodynamic variables. Okay, so Q is the potential, and you write it as PV by KT. Okay, and the relation between Q and the partition function is given as Q equal to ln Q. So that means now you can write Q as this expression here. Okay, so now, so you can understand, based on whatever type of particle you are talking about, you can write a general expression, okay, where the different values of A corresponds to different kinds of particles. So if A is -1, it's the Bose-Einstein case. If A is +1, it's the Fermi-Dirac case. If A is 0, then it's the classical particle or the Maxwell-Boltzmann case. Okay. So based on the different values of A, you can have different expressions for the Q potential. And you can understand Q potential is actually basically giving you a relation between the number distributions or how the particles are distributed and with the thermodynamic variables like pressure, volume, temperature, and so on. Okay, so this is a very important relation. Okay. Okay. Now one can also define, the average number of particles or the average energy in terms of the Q potential by these relations. Okay. And so I'm not going into the derivation again because this is something we have already discussed before. Now this, what you have here is called the mean occupation number. Okay. This is your expression of the mean occupation number. And basically, when you're writing the average energy, you are multiplying the mean occupation number for each energy level with the respective energy and then doing a sum. Okay. That's how you're finding the average energy of your system. Now, this is same as, so whatever you are finding here, it's same as doing this. Okay, so this is your general definition. So here e to the power minus beta E by Z is your probability of for being in that particular state. And then based on whatever observable you're trying to find the average of, you multiply the individual values with the respective probabilities and then do a sum. That's the typical way of finding an average or a expectation value, right? And this is same as doing this summation. Okay, this summation. So from here you can say that you can write this average n as summation over E NE, where this term here is the mean occupation number. Okay, it tells you on average how particles get distributed into different energy levels. Okay, and based on what kind of particle we're talking about, whether they are fermions or bosons, the distributions would vary. Okay, so how do you define the mean occupation number? This is the definition. So here you replace what is Z. Z is nothing but e to the power mu by KT, right? Where mu is your chemical potential, right? So this is your definition of the mean occupation number. Now, if you want to plot for different values of A, you would have all these different plots. So you can see that for a Fermi-Dirac case, it saturates to a value less than n, because for a Fermi-Dirac distribution, n epsilon can be either 0 or 1, right? So the average comes out to be below 1. And this is how it looks like. And then for bosons, you can see that as you go, so as mu, which is the chemical potential, as it approaches epsilon, which is the, in this case, you would say that the lowest energy state. So as it goes close towards 0, you would see that n epsilon blows up. So it almost diverges, right? So this is associated with the condition of Bose-Einstein condensation, which we will read in detail today. Okay. So, and you can see there is no distribution below, like where epsilon minus mu is less than 0. So there is no distribution here for the bosons, right? And then for Maxwell-Boltzmann, this is a typical distribution that you get. At high temperatures, as you can see, they all merge to similar values. Okay, this is the classical limit where this quantum nature gradually becomes negligible. Okay, the effect becomes negligible. Okay. Now, the question is, where does quantum effect set in? And this is something which we had also discussed before, but briefly. But if you have to quantitatively talk about what is the number or what to look at to say that, okay, this is here quantum effects are significant and here it's not significant. How do we say that, right? So you can consider the case that, so here we shall now investigate in detail the physical behavior of a class of systems in which, while the intermolecular interactions are still negligible. Why? Because we're talking about ideal gas. Okay, so intermolecular interactions we are not considering, but the effects of quantum statistics. What do you mean by, like, what is the underlying, feature that we're talking about? So when we talk about quantum statistics, we are considering that this arises from the indistinguishability of the particle, and that, so we want to find, though it's an ideal gas where there are no interactions, even then the quantum nature of the particle, the fact that they are indistinguishable, where does it become important? Okay, that's the limit that we want to find. Okay, so this means that the temperature T and the number density N of the system no longer conform to this criteria here. So that means if N lambda Q is less than 1, okay, so this would be your typical, can understand, it's the low, what do I say, basically high temperature or low particle density limit, right? So that limit is associated with the classical domain. Okay, so when this condition does not hold, okay, so when your system no longer conforms to this criteria, when this condition does not hold anymore, then we are actually going towards the quantum regime. Okay, so here lambda is called the mean thermal wavelength or thermal de Broglie wavelength of the particle. Okay, so N lambda cube turns out to be a very appropriate parameter in terms of which the various physical properties of the system can be adequately expressed. So what happens is, in the limit of N lambda cube, so in the limit of N lambda cube tending towards 0, all physical properties go over to the classical counterparts. So this is your high temperature or low density, low number density limit. Okay, so if you find, suppose for a given system, the typical temperature that you are working with, and you can find the mean thermal wavelength, and the number density, so you can actually find this term. And if you see that it is a very small value, it tends towards 0, then typically you are in the classical regime. Okay, for small but not negligible values of N lambda cube, the various quantities pertaining to the system can be expanded at power series. Okay, and from these expansions, one obtains the first glimpse of the departure from classical behavior. So if you do a power law expression, and then based on what are the different, what do I say, terms that you include, you would see that you would gradually see the departure from the classical behavior. So when N lambda cube becomes of the order of unity, okay, so when that means when it's no longer much smaller than 1, okay, it tends towards 1, there the behavior of the system becomes significantly different from the classical one. Okay, and it is characterized by the quantum effects. So for any system, if N lambda cube, this term, okay, where lambda is your thermal wavelength, mean thermal wavelength, so this term would allow you to quantify whether quantum effects are significant or not. Okay. Now talking about ideal Bose gas. Okay. So we saw that the potential, Q potential, is given as PV by KT, and that is equal to ln capital Q, where Q is your grand canonical partition function. Okay. Now for the Bose gas, you would put A equal to -1, right? So if I go back, this was our general expression, right? So if I go back to this description, this was our general expression. Now, if you put A equal to -1, you would get the Bose-Einstein distribution. So now we'll be talking about that. Okay. Till now, we were talking about the general, different ways, like the general description behind quantum statistics. Now we are looking into particularly the Bose-Einstein distribution. Okay. So you put A equal to -1. So this is the relation. PV by KT is equal to ln Q equal to this. Again, you can write N which is like the total number of particles or the average number of particles. It's summation over epsilon n epsilon. So this term here is your mean occupation number. Okay. Z minus 1 e to the power beta epsilon minus 1. Now, as we discussed, for this to be well defined, see, this cannot be a negative quantity. Otherwise, so n becoming negative, it actually makes no sense, right? Or the mean occupation number being negative, what will it mean physically? Nothing, right? So this has to be, so for this to be defined, z to the power minus 1 e to the power beta e should be greater than 1. Okay. So that again means z e to the power minus beta e should be less than 1. Okay. Where z is your fugacity, which is given as mu by kt. So what is this telling you? So now you can explicitly write z as e to the power mu by kt. So that will tell you e to the power mu minus beta into epsilon should be less than 1, right? So this is again telling you that mu should be less than epsilon, which implies that the chemical potential must be lower than the ground state energy. Okay. So if in a system where you're talking about the Bose-Einstein distribution, there are different energy states. So your chemical potential should be lower than the ground state energy. Okay. So that means if you're talking about free particle where the lowest energy can be 0, okay, in that case, your mu, that is the chemical potential, should be less than 0. Okay. And in this limit, what would be the value of Z? So Z would therefore vary from 0 to 1. Okay. So as you go towards 1, you are going towards the more towards the quantum regime. Or what do I mean is, so you would gradually see, like as we go towards, as Z goes towards 1, that's typically the condensation regime that would come up. Okay. So now for large V, considering the spectrum of single particle states as continuous, what we can do is we can change this summation to integration. So basically you're considering that you have a large volume, and then the energy, different energy states are like closely spaced. So you can actually do an integration of over the different energy states. Okay. So PV by KT, this is your general expression. And from here, you can actually go to an integration where you do an integration from 0 to infinity. And now what you do is you're considering free ideal gas, right? So your energy would be given as, so for any free particle, in that case, your energy would be given as P square by 2m. But you can also have other distributions. So this is a general expression that we are writing. So P is given as KT by A integration over 0 to infinity, ln this term. And now, so basically when you're going from summation to infinity, the integration, what are you doing? You're basically doing an integration over the phase space volume, right? So that's why you're writing it as 4 pi p squared dp divided by h cube. What is h cube? H cube is the smallest phase space volume occupied by a single microstate, right? So this is how you go from summation to integration. And now if you do integration by parts, so this term would go away. So what would remain is this. So now pressure is related to, related by, or is described by this expression here. So what is important, you see that if energy epsilon has a momentum dependence, okay, so that functional form is important. And then the type of particle that you're talking about is important. The chemical potential is important. Okay. So these are the terms that those are important. So for Bose gas, A is -1. So you can put A as -1. Okay. And then based on whatever particle you're talking about, so whatever be the energy dispersion relation, based on that, your expression for pressure would change. Okay. So for non-relativistic free particle, we know that energy is given as P square by 2m. Okay. So based on this, you can actually define a density of state which talks about how many, density of state basically is telling you how many particles in a energy state from epsilon to epsilon plus d epsilon, right? And how do you basically do it? So you see that, epsilon is p square by 2m. So p square is given as 2me. P is root over of 2me. So from here, you get this term here. Okay. And you're basically doing an integration over the phase space volume, but now you're writing it in terms of energy. So initially you had 4 pi p squared dp. Now you're changing from p to epsilon energy. Okay. And this is what you get. So this is your density of states. Right. So we, however, note that by substituting this expression into our integrals, we are inadvertently giving a zero value, okay, zero weight to energy level epsilon equal to 0. Right? Because what is it telling you? So if your energy epsilon goes to 0, your density of state goes to 0. So physically it means that there are no particles in the zero energy state, right? While we know that that is not the case, right? So it's wrong, because in a quantum mechanical treatment, we must give a statistical weight unity to each non-degenerate single particle state. Okay. And if you consider the fact that now you're talking about Bose gas, so you can have, so under certain conditions, you can have many number of particles in the zeroth state, right? So that means we have to explicitly consider the case where epsilon goes to 0. This is true when epsilon is not equal to 0. But when epsilon is equal to 0, we have to explicitly consider that term. Okay. So now, given the density of states, what you can write, you can basically go from, so here initially you were doing the integration in the momentum space. Now you can go to the energy space. Okay. So this is what you get. So now you have written in the energy space. Now here you can see the first term. So this is same as what you had written previously in terms of momentum, right? But this term here comes because of, so this term is associated with the case when epsilon is equal to 0. Okay. So this corresponds to the epsilon equal to 0 case. This corresponds to all the other conditions when epsilon is not equal to 0. Okay. And this is what you get. Similarly, you can write n by v. And even in the n by v case, this is your general expression, right? And then you have this extra, this term coming up. Why is this coming up? This is coming up because of epsilon going to 0. This is your epsilon equal to 0 state. Okay. So how do you do it basically is that if I go back, see here, if you consider this expression, okay. So here, if you put epsilon equal to 0, what will happen? This would become e to the power 0 is 1. So you would get 1 by z to the power minus 1 minus 1. So this is nothing but writing 1 by z minus 1. So you can take z above. And this will be like 1 minus z. Right? So z by 1 minus z is nothing but n0, which is the number of particle in the zero energy state. Right? So that means this term here, okay, can be written as n0 by v. Okay, where n0 is the number of particles in the zero energy state. Similarly, this term comes because of the epsilon equal to 0 term. Okay, so this is your expression for pressure, and this is the number density n by v. For z much smaller than 1, which corresponds to the situation not far removed from the classical limit. Okay, so when z is much smaller than 1, then you are in the classical limit. And there you can see that these effects are not very significant. Okay, each of these terms is of the order of 1 by n and therefore negligible. However, as z increases and assumes the value closer to unity, okay, so now you're going towards the quantum regime, the term z by 1 minus z. So what happens when z tends to unity? You can see this value becomes very small, right? The denominator becomes very small. So the overall term becomes quite large, right? So when z tends to unity, the term z by 1 minus z into v, which is identically equal to n0 by v, where n0 is the number of particles in the ground state, that can become a very significant fraction of n by v. So that means when z tends to unity, you cannot ignore the epsilon equal to 0 term. or the zero energy term. Okay, this plays a important role in that case. Okay. This accumulation of macroscopic fraction of particles into single state epsilon equal to 0 leads to the phenomenon of Bose-Einstein condensation. Okay. So what is it telling you? So as Z tends to 1, this value keeps on rising, which tells you that N0 keeps on rising. What is N0 or N0? So N0 is the number of particles in the zero energy state. So that means as Z tends to 1, the number of particles in the zero energy state keeps on rising, right? And that phenomena is called the Bose-Einstein condensation. Okay. Now you can understand that while this keeps on rising, ln of 1 minus z do not change much. Okay, so in that case, this can be ignored. I mean, this is not so, does not play much of a significant effect because of the logarithm term that is involved. Okay. So now you can actually solve for the Bose-Einstein, Bose gas. So what you can do is you can explicitly write this expression. So P by KT would be given by this relation here. Okay. So here, this integral, okay, basically the general way of writing it is using this Bose-Einstein function, okay, which takes up this form. And that is what is also present here. So basically you can rewrite it using this expression. So P by KT becomes 1 by lambda cube G 5 by 2 Z. Okay. So here Z is your fugacity. Okay. And lambda cube is your mean thermal wavelength. Okay. And then you have again expression for N minus N naught by B. So now what you have done is you have transferred this term to the left hand side. Okay. So N minus N naught. That's how N minus N naught has come on. Okay. So this is what you get. So here you can say that now you can define a function which is actually a series of all these terms. Okay. And this is called the Bose-Einstein function. And you can write the pressure or the number of particles and all of that in terms of this function. Okay. The internal energy again. So you know the relation between the grand canonical partition function and the internal energy or the average energy, right? So this is the relation. So here again, you can use the same expressions, okay, to write an expression for the internal energy. Okay. So you're writing all of them in terms of now the Bose-Einstein function, okay, which is a series. Basically, this is the series. Okay. So from here, if you try to find an expression, so you have an expression for P by KT, you have an expression for U. Okay. And from there, you can actually get back the same relation. So this is something which we had initially solved also for the case of like free, non-relativistic particle. And again, you have got back the same equation. So everything seems consistent, right? Okay. So N minus N naught by V is given by this relation here. So N minus N naught by V is equal to 1 by lambda cube G 3 by 2 Z. Okay. Now, what is this telling us? So here, N minus N naught means the number of particles in the excited state. Total particle minus particle in the ground state equal to number of particle in the excited state. So Ne becomes equal to V into 2 pi m kt to the power 3 by 2 by h cube G 3 by 2 Z. Okay. So basically you have written this, explicitly, and this is the same. So Ne is the number of particle in the excited state where energy is not equal to 0. Of course, unless Z gets extremely close to unity. Okay. So gradually, as Z tends to unity, Ne tends to N. Okay. Now, because Z has an upper limit, right? We saw that Z ranges from 0 to 1. What is this telling you? This is telling you that now the Bose-Einstein function also should have an upper limit, right? So the function g 3 by 2z increases monotonically with z and is bounded. So what does it mean? So that means is maximum. And when will this term be maximum? This will be maximum when z is maximum. And the maximum value of z is 1. Okay. So now if you put g 3 by 2, 1, then you are putting all this, numerators become 1. And you can solve it further. So what you get is this. So now you get this function. Okay. And here, this sets the maximum value of NE that one can get. Right? So hence for all z of interest, g 3 by 2z should be less than equal to zeta 3 by 2. Okay. And that would give you the maximum value of n. So what this tells us that for given v and t, the total number of particles in all the excited state taken together is also bounded, and the limit, the maximum value, is given as NE should be less than equal to V into 2 pi m kt by h square whole cube. Okay, which is nothing but, so this entire term comes from the thermal wavelength. You have V here and you have zeta 3 by 2. Okay, so this comes from the maximum value of the Bose-Einstein function. Okay, so now this is the maximum number of particles that can be there at a given in the excited states. Okay, so now two cases can arise. So first is when n is less than n epsilon. So if the total number of particle is less than n epsilon, Ne, okay, and what does Ne depend on? So Ne depends on the temperature, as you can see, right? It goes as T to the power 3 by 2. It depends on the volume. It depends on, like, other terms are called constant. So these are the main terms that govern your, Ne. Okay. So now if your total number of particle is less than Ne, all particles are distributed over excited states, and hence Ne should be comparable to n. Okay, so n less than Ne, that means everything goes to the excited state, and Ne is given as Ne is comparable to capital N or total N. Okay, so number of particles in the ground state is less. When n is greater than n epsilon or Ne, what happens? So now there is an upper limit to how many particles can be there in the excited state. So whatever extra term you have should go into the ground state. Okay, so all extra particles go into the ground state. So from here you can see that this is your relation of Ne with T. It goes as T to the power 3 by 2. This is your maximum number of particles in the excited state, and N naught, which is the number of particle in the zero state, is given as total number of particle N minus Ne. Okay. So you can define Z as N naught by N naught plus 1, which is given as 1 minus 1 by N1. Okay. So that means as you go closer to unity, okay, as the Z value goes closer to unity, the number of particles getting accumulated at the ground state keeps on rising. Okay. So now with this knowledge, okay, what we want to do is we want to see physically what is happening. Okay, so suppose you have some capital N number of particles, and you know the temperature, you know the number density and all of that, in the sense that you know the volume, suppose, okay, and you know the number, the temperature, and you can actually use this expression. Okay, So you can use this expression to find Ne, which tells you the total number of particles that can be present in the excited state. So whatever remains, N minus Ne, would be the number of particles in the ground state. Okay. So now, as your, uh, number of particles, the total N, if it keeps on rising beyond Ne, beyond the maximum value of Ne, what would happen? All this large number of particles, extra particles, would start accumulating in the single particle state epsilon equal to 0. Okay. So this phenomena of, macroscopically large number of particles accumulating in a single particle state is generally what is called the what is called the Bose-Einstein condensation, BEC. Okay. So that means if you keep on increasing the number of particles in the system beyond a certain value, things will start accumulating in the ground state. And that phenomena is called the Bose-Einstein condensation. And in a certain way, this is similar to, so you can compare it with the familiar process of vapor, condensing into liquid state. Okay. But there are some very important differences. So first is this kind of, condensation from vapor to liquid kind of condensation. This happens in the physical space, like in the coordinate space. Okay. While the Bose-Einstein condensation that we are talking about happens in the momentum space. Okay. And another important point is that, so Bose-Einstein condensation is purely a quantum mechanical effect. Okay. It's not coming because of any interaction between particles, because we have not considered any intermolecular forces yet. Okay. It's an ideal gas. But even then, this is coming because of the underlying inherent quantum origin, quantum nature of the particles. Okay. Those are the major differences from a typical, condensation. Okay. So the condition for the onset of Bose-Einstein condensation is given as N greater than this limit. Okay, so this is something you should remember from the discussion that we have been having. Okay, so the condition for the onset of the Bose-Einstein condensation is given as N greater than Vt to the power 3 by 2. So this term comes from the thermal wavelength, and then you have zeta 3 by 2. Now, if you hold N and V constant, okay, so N and V constant and vary T. So then what would happen? Basically, you would see that there is a temperature below which condensation happens. Okay, so for T less than Tc, you start getting condensation. This Tc is called it's that critical temperature, okay, where below which Bose-Einstein condensation happens. So Tc is the characteristic temperature that depends on the particle mass and the particle number density in the system. Accordingly, for T less than Tc, the system may be looked on as a mixture of two phases. Why? Because for T less than Tc, condensation starts happening. So that means now you have two states. One is a normal phase, okay, where your, so normal phase means your particles get distributed based on like T to the power 3 by 2 relation, okay, and they get so they are getting distributed in the excited state. And then there is a condensed phase which happens with all the particles that keep getting accumulated in the ground state. So there are two phases that are there. One is a normal phase, another is a condensed phase. Okay, and that happens for T less than Tc. Okay. So now if you want to plot how Ne or N naught, or this ratio of Ne by N or N naught by N, how does it vary with temperature? So you would see that this is how it would look like. So below a certain temperature, the number of particles in the ground state keeps on rising. while the number of particles in the excited state keeps on decreasing. So this is the point where, so it rises and then it gets saturated, and this is your point of maximum number of particles in the excited state, and that is also the point just beyond which particles start accumulating in the ground state. So one can also write how Z varies as a function of V by lambda cube. Okay, so you can see that. So this is your condensation phase where this region is your like the quantum regime or the condensation regime where Z is 1, while at the higher limit you would see Z goes as V by lambda cube minus 1. Okay, so V here is the volume per particle. So V by lambda cube to the power minus 1. Okay. Yeah. So this is your more of the classical regime. Okay, and this is your quantum regime. Okay. So now this is your relation that we had initially derived, right? P by KT is given by this relation here, where you can write it in terms of the Bose-Einstein function. So for T less than Tc, what happens? For T less than Tc, your Z is 1. Okay, so you can put Z going to 1. Okay, now when you put, so we just saw that G is your Bose-Einstein function. Now G 5 by 2 Z, and then if you put Z equal to 1, that would give you the zeta function, right? So now P is written as KT by lambda cube into zeta 5 by 2. Okay, so what is this telling you? This is telling you that T is proportional to 5 by 2. Why? Because you have a T here and you have lambda cube here. So lambda, this, thermal wavelength has temperature there, right? So the overall dependence of pressure on the critical temperature is given as T to the power 5 by 2. And it is independent of V. Okay, so which implies infinite compressibility. Right. So now at the transition point where T is equal to Tc, so now you can replace T by Tc. Okay, and explicitly this is how the expression will look like. So this is your expression for pressure at the critical temperature. Okay. For T greater than Tc. Okay, now what happens as you go to higher frequency, higher temperatures, T greater than Tc. So what you can basically do is, this is your basic relation, right? P by KT is G 5 by 2Z by lambda cube. So you can replace lambda cube in terms of G. How do you do it? So basically you can use this relation. You can use this relation. So in the limit where like T greater than Tc, you can approximate N minus N naught as N. Okay. So N by V would be given as G 3 by 2Z by lambda cube. So from here you can find an expression for G, find an expression for lambda cube in terms of G. Okay, and you can replace it there. Okay, so if you do that, so you can replace the value of lambda cube, and this is what you would get. So P by KT is equal to G 5 by 2Z by lambda cube, and in place of lambda cube, you can write it in terms of G 3 by 2. Okay, so this is the expression. So this is your expression of pressure at temperatures beyond the critical point. This is your expression for pressure below the critical point. Okay, that's how you can try to find all the different thermodynamic variables associated with it. Okay. And now you know the relation between internal energy and the grand canonical partition function. So that is given as this derivative, right? Minus del del beta of ln q. So you can write the derivative in terms of capital T, and this is how it would look like. And here again, so now because you're doing the internal energy, you have to do this derivative here. Okay. And this is how it turns out to be, right? So 3 by 2 KT, V by lambda cube, G 5 by 2 Z. So here for T less than Tc again. So because we have to look at both the limits, okay? At T equal to Tc, we know that, so below Tc, what happens? Condensation happens. Beyond Tc, condensation do not happen, right? So for T less than Tc, what happens? So here Z is 1. Okay, so you can basically replace G by eta. Okay, and this is how it looks like. So this is again proportional to T to the power 3 by 2. So what you can do basically is you can take a, so again you can write explicitly, convert lambda cube in terms of G, and then because Z is 1 in this limit, so in this limit you can consider Z to be equal to 1. Okay, so then you can convert G, the Bose-Einstein function, into eta, and then replace lambda cube by this. Okay, so this is how it would look like. So here you can see CV by NK comes out to be 1.925, which is significantly higher than the classical value, because in classical value we know that the specific heat is given as 3 by 2 NK, right? So that is 1.5, but here it's larger than the classical value. Okay. Now again, if you want to do at the high temperature, so T greater than TC, what happens? Again, you can replace, lambda cube. So you can replace lambda cube by this relation here. Okay, and then include the fact that, so you can use this relation del T, because you have to do a derivative, right? You're finding the specific heat, so del T of G3 by 2Z. So this is how the derivative looks like, and that you can put in there. So this is your expression. Okay. So from here, see, these relations are very useful. So you can just use them back, and you get an expression for CV by NK. So you get an expression of CV by NK for T greater than TC. Okay, and for T less than TC, this is your expression. It's a value larger than the classical limit. So if you want to plot CV versus CV by NK versus T by TC, you would see that when T equal to TC, that is at the critical point, your CV is higher. CV is higher than the classical limit. So classical value is 1.5. Okay, CV is 1.9. Okay, and then at high, temperatures, it saturates, just flattens out, and at low temperatures, okay, so T less than TC at low temperatures, again T goes as T to the power, CV goes as T to the power 3 by 2. Okay, where are you getting that? So basically you see you have a T, you have a lambda cube terms coming in. So from there you can see that at lower temperatures, your CV goes as T to the power 3 by 2, and at higher temperatures, this is how it looks like. So it flattens out, and then at the critical point, T is equal to TC. There the ratio of CV by NK is given as 1.9, higher than the classical regime, classical value. Okay. So based on what we have been discussing so far, we try to solve some questions now. So here it says that Bose condensation occurs in liquid helium-4 kept at ambient pressure of 2.17 Kelvin. At which temperature will Bose condensation occur in helium-4 in gaseous state, the density of which is 1,000 times smaller than that of liquid helium? Okay, so what is it telling you? It is telling you that liquid helium has a critical temperature given as 2.17 Kelvin. Now you're talking about liquid helium in the gaseous state whose density is 1,000 times smaller. So in that case, what should be the critical temperature, right? That's the question. So whenever you see, I'm giving you some time to think about what we have been discussing so far. You want to find the critical temperature. So you need to think about the different relations that relate critical temperature to different, actors. So, it depends. So based on whatever system you're talking about. Based on that, you can choose which, I mean, how does the critical temperature T vary with the density, right? So whatever system you're talking about, based on that, what's the density of the system, and how do you choose the relation? Okay, this is something which I've already discussed. So for one system, you know how T goes as, or TC goes with density. If you know the relation, then you know the density for a certain system. You want to find the density for another system, which is 1,000 times smaller in density. Okay, that's the relation. So remember or try to find what is the relation between critical temperature and uh, T, like critical temperature TC and density. Okay, that's the question. So I'll give the relation. And as you solve, you can just look into it. So this is basically the relation, right? So this is the relation, right? Now, what is this telling you? Or from here, maybe this one, right? This is the relation that you have got. So TC is related to, so H, M, these are constants, and then, okay, K, N by V is there. So N is the total number of particle, V is the volume. Okay. So N by V is your number density, right? Rest all the other terms are constants, right? So what is it telling you? So it is telling you that your TC goes as, or is proportional to, so if I write small n as the number density, it goes as T to the power, n to the power 2/3. So TC is proportional to n to the power 2/3, where n is your number density. Okay. So now based on this, can you try to answer this question? Yeah, okay, it's already there. So yeah, try to answer the question. So if your density or number density, suppose n, if it decreases by 1,000 times, your TC is expected to decrease 100 times, right? Because it goes as n to the power 2/3, right? So now if your initial, critical temperature, or the transition temperature, if the initial temperature was 2.17 Kelvin, what will be your TC for the vapor state or the gaseous state, which is 1,000 times smaller density? So that means it's 100 times smaller, right? TC will be 100 times smaller. So that means it will be 0.0217 Kelvin, right? So now you can change it to millikelvin and it would be given as, so 0.0217 Kelvin is equal to 21.7 millikelvin, right? So the answer is B. Okay. Now let us look at another question. So it says that there is a large number n of ideal bosons, each of mass m, and they are trapped in a 3D potential, which is given as half m omega square r square. The bosonic system is kept at temperature T much smaller than Tc. Okay, the chemical potential mu satisfies which of these different criteria? Okay, so you have bosons, ideal bosons in a three-dimensional potential. Okay, so it's a, as you can see, it's a harmonic potential, right? Half m omega square r square, three-dimensional harmonic potential, and it's a bosonic system. It's kept at a temperature much smaller than Tc. What does that mean? That means condensation will be happening, right? Z is much small, T is much smaller than Tc. So here, what should be the criteria that the chemical potential should satisfy? Just think of the criteria. Okay, so, mu, the chemical potential comes in terms of the fugacity, right? Z. Now think what should be the typical value of Z, okay? Or what limits the value of Z? When we are talking about Bose-Einstein distribution, what limits the value of Z? What is the value of Z in which it ranges, right? And then from Z, you can actually find a relation between, you know, the chemical potential and the energy states, right? This is something which we have already discussed. So I'll give you some time to think and try to find an answer for this. So what happens when T is much smaller than Tc? Okay, what is the value of Z? And then, so consider the fact that if you have a bosonic distribution, okay, what is the relation between the chemical potential and the different energy states, right? So for this system, what would be the typical, what is the ground state energy? What is the maybe next excited state energy? How do you define that, right? It's a three-dimensional harmonic potential. So you see that for a three-dimensional harmonic potential, the ground state energy is, so for each degrees of freedom, you have a half h cut omega. So the ground state energy would like, I mean, you're talking about a quantum uh, system. So here you would have a ground state energy at, for each direction. If you have half h cut omega, for three of them it would be like 3 by 2 h cut omega, right? So 3 by 2 h cut omega is your ground state energy, right? Now if we look at the relation, okay, so or if you look at how the number density, even if you look at how the mean occupation number varies, even there you can look at it. But we did see that from the mean occupation number expression, we have this 1 by z to the power minus 1 to the power beta u minus 1 kind of expression, right? So there, from there, what did we see? So if I go back, we did see this expression that for Bose-Einstein distribution, very early in the discussion, we saw that mu should be less than epsilon. Okay, so the chemical potential must be lower than the ground state energy. And this is coming from this expression of your mean occupation number itself. For this to be defined, okay, z e to the power minus beta epsilon should be less than 1, which tells you that mu should be less than epsilon. Okay, now for the question at hand, okay, what is the ground state energy? The ground state energy is given as 3 by 2 h cut omega, right? So that is directly telling you now that the bosons are trapped in a three-dimensional harmonic potential. So the ground state is given as 3 by 2 h cut omega. Now the chemical potential should therefore satisfy the condition that mu should be less than equal to the ground state energy, which is 3 by 2 h cut omega. So the answer here is A. Okay. Now this is another question. So here you have to see, we were talking about Bose-Einstein distributions, right? We're talking about bosons. Now in nature you can have there are different bosons or different particles with there are different particles with integral spins. The photons, which is like the quanta of energy, so you can say that photons are bosons. Okay, they have integral spins. So you can define, or you can write a distribution for photons in terms of the Bose-Einstein distribution. Okay, so here the question says that how many photons are there in 1 cc of radiation at certain temperature given. Okay, and you have to find the average energy given this integral. So this is a very, it's a little complicated integral, like, so the values are already provided. So you have to first find how many photons are there, and then you have to find their average energy. Okay, so in this case again we would make use of the fact that photons have Bose-Einstein distribution. Okay, and based on that we try to define how photons are distributed across different, so if you have photons at different frequencies, how would they get distributed, and then from there you would try to find the total number of photons and then the average energy. Okay, I'll just give a couple of minutes to actually think how this can be solved, and then we'll try to discuss the solution. So number of photons per unit volume in some frequency interval nu to nu plus d nu is given as this. So it's also coming from the Planck's law. Okay. So this is the number of photons per unit volume in some frequency interval. So now if you want to find total number of photons, how will you do it? So you'll do an integration over all the possible values of frequencies. Okay. So total n is given as 0 to infinity n nu d nu. Okay. And this is an integration. So here this integral, it's a well-defined integral. The value is already provided. So you can use that value. Okay. And that would give you the total number of photons. Right. Now, once you have the total number of photons, this is the first part, how many photons? Okay. Now, it said what is the average energy? So total radiation per unit volume is given as this relation here. So we already know this from, our understanding of like when you talk about radiation. So E is proportional to 3 to the power 4, and this is how the proportionality constant looks like. So now you know the total radiation energy and you know the number of photons. So if you want to find the average energy per photon, it would be given as E by N. And from there, you can get the average energy per photon. Okay. So once you know this distribution, this question is quite trivial, right? So you already, so other things are like quite trivial. You can always like define and try to find the average energy and all of it. The main point here and why this question is important or why did I include it here is because how did we get to this expression, right? How did we get to this distribution, which tells us how many photons are there per unit volume in this frequency range? So how did we write this expression? So here we have used the Bose-Einstein distribution. How? So if you want to find the number of photons, suppose in some energy interval epsilon to epsilon plus d epsilon, how will you write it? So you will consider that these are bosons, so they would have a mean occupation number, which will be given as e to the power alpha e to the power epsilon by kt minus 1. So this is 1 by this term is your mean occupation number, and then you have some degeneracy which is coming because for each energy, okay, which is given as ge. Okay, so for photons, you can just consider the, so here ge is not really degeneracy. It's like how many, what do I say? It's like the density of states. Okay, so how many states are possible in the range epsilon to epsilon plus d epsilon? Okay, so if you have to write it, you can write it in the energy space. You can also write it in the momentum space. So you can write gp dp is nothing but, so typically it is 4 pi p squared dp into v by hq. And now because it's photon, so you have a plus and a minus coming up. Okay, so there is a degeneracy of 2. So that's why you get v by hq 8 pi p squared dp. Okay, so now if you want to write g nu d nu, what will you do? So you can go from the momentum space to the frequency space. Okay, so you know that energy, you can always write energy as equal to h nu, right? So from there, from that relation, you can go from momentum to frequency, and this is how the distribution would look like. Okay, so this is your frequency distribution. Now here, why do you set alpha to 0? Alpha, you can understand alpha is associated with the fugacity, right? E to the power mu by kt, and now you have written mu by kt as alpha, right? So alpha, why do you set it to 0? Because when we are talking about photons, so you can absorb certain number of photons and then release certain number of photons. The number of photons by itself is not conserved. Okay, so that means in the initial stages where we were solving for the grand canonical partition function, if you remember, alpha came in as your Lagrange multiplier when you had considered capital N to be, so you had considered that your n is like there is a constant, right? So summation over ni is equal to n, like we wrote that, and associated with that there was a Lagrange multiplier alpha. But now for photons, because that is not conserved, so your alpha is set to 0. So what do you get? So now alpha is set to 0, so e to the power alpha becomes 1. And e to the power epsilon by kt minus 1 can be written as e to the power h nu by kt minus 1. And g nu d nu is nothing but this value here. Okay. It's like the density of states for where your frequency varies from nu to nu plus d nu. Okay. So if you include that here, this gives you the number of photons per unit volume in this frequency range. So that's how you can, like in this physical world, that's how these distributions become useful. So here you are writing a distribution for photons using the Bose-Einstein distribution. Okay. Because they have integral spin, so they can be considered as photons. They follow the Bose-Einstein distribution. And so using this typical, this is a very standard way of defining a density of state or defining the number of particles. So using this, you can actually write this expression. Once you get this, next things are trivial, but this is the step where the distribution, the knowledge about the Bose-Einstein distribution comes. Okay. Now, next question says that an ideal Bose gas in d dimension obeys the dispersion relation given as energy epsilon goes as a k to the power s. So k is your momentum. Okay. So a into k to the power s. A and s are constants. For Bose-Einstein condensation to occur, the occupancy of excited states is given by this relation here. Okay, so Ne, that is the number of number of particles in the excited state, that is given as Ne. Okay, where C is a constant. And so for Bose-Einstein condensation to occur, this thing should remain finite even for mu equal to 0. Okay, because Ne should be defined, right? So it should be finite. It should be defined even when mu is equal to 0. Okay, so when can this happen? That's the question. Right. So this is your expression of number of particles in the excited state. Right. So here it says if you put mu equal to 0, what would happen? So it will be epsilon d minus s by s by e to the power beta epsilon minus 1. Right. dE. And this should be defined. Now for this to be defined, right, what happens? So if you put mu equal to 0, you get an expression like e to the power something. So d minus s by s, e to the power d minus s by s divided by epsilon to the power d minus s by s divided by e to the power beta epsilon minus 1. Right. So this is your expression, right? Now here you can see that the integral runs from 0 to infinity. What happens when you put epsilon going to 0? That means at the 0 energy state, what happens? So this becomes 1. So below in the denominator, it becomes 1 minus 1, which is 0, right? And above also, if you put epsilon to be 0, this becomes 0. So basically it takes a 0 by 0 form, right? So for this integral to be defined, if you remember, our basic understanding of limits, whenever we had, so in the limit of epsilon tending to 0, if you have a 0 by 0 form, how do you find the limit? So we used to keep on, for a ratio like this, 0 by 0 form, we used to keep on, doing derivatives for the denominator and the numerator, right? The L hospital rule. So we used to keep on doing the derivatives till we get a, defined value, right? So what this is telling you is, so now for this to be defined, when mu is 0, this would have a 0 by 0 form because you have a lower limit of 0. Okay. So for this to be defined in the limits of epsilon tending to 0, while mu is also 0, how will you define it? So you do multiple derivatives of the numerator and multiple derivatives of the denominator. Okay. So each time you do a derivative here, because you have a power, right? It's in the exponent. So basically you have to do d minus s by s times derivative, right? So what you will get as a coefficient at the front would be like d minus s by s factorial, right? Now, for that quantity to be defined, what does that mean? So if you have if you have a term, right, like d minus s minus 1 to be defined, right? So for this to be, and then you have a, so if you do all multiple number of derivatives, you would have a factorial like this. So this will be defined when? This will be defined when d by s is greater than 1, right? This has to be a non-negative quantity, right? So that is already telling you that the answer here should be C. D by S should be greater than 1. Now you can also cross-check it with the results that we have initially found. So we know that Bose-Einstein condensation is possible in 3 dimension, and for massive particles, materialistic particle, massive particle which have defined mass. So we know that G goes as e to the power half, right? Density of state goes as epsilon to the power half. So that means d minus s by s is equal to half, and for 3 dimension d is equal to 3, right? So this tells you d by s here, as you can see, is greater than 1, right? Again, if you do it for the massless particle, where g goes as epsilon square, your d by s comes out to be 3, which is again greater than 1. So you can see that the results that we already know is also consistent with the fact that for this to be defined, the answer should be C, which is d by s should be greater than 1. Okay. Now also be careful. So suppose here, like one can ask, in this case, you're getting epsilon to the power half, here you're getting epsilon square. How? Right? Why? So this is depending on the energy dispersion relation. For a massive particle or a particle with some different mass, we know that so epsilon energy is given as p square by 2m, right? P square by 2m. For massless particle, epsilon energy is given as P into C. So that's how the dispersion relations are different for both the cases, right? And that results in this difference in the density of states. Okay, so be careful about how we get there. So basically, if this is how you define the total number of particles, okay, so you're doing an integration over the phase space volume. So you have 4 pi p squared dp. This comes from the mean occupation number. Okay, and you have a v by h cube outside the, so you have a v by h cube outside the integral. So now you can, so here what you see is you have a p squared dp, and then you can change this p squared dp, which is in terms of the momentum, you can change it in terms of energy. So if you consider E epsilon goes as P into C, so you can write it as, just write P in terms of, like, use the relation between momentum and energy. Okay, so do a change of variable. So then this is the relation that you would be getting. So you get an epsilon square here, as you can see. Okay, so that's how this epsilon square comes out. So based on the dispersion relation that, or the relation between momentum and energy, you would get different density of states. Okay. Also, it would depend on what dimensions we are talking about. So here it's in 3D. That's why. So it's in 3 dimension. That's why you have 4 pi p squared dp. Okay. It's in, if it is in 2 dimension, you would have a 2 pi p dp kind of phase space volume, right? So based on what is the dimension of your phase space, your element, volume element, like, I mean, how do you define the hypersurface, or how do you define the hypervolume, that would change, okay? Whether it's 3D or 2D. So accordingly, your density of states would change. So be careful about that. Okay. Now there's another question which says that consider an ideal Bose gas in 3 dimension. Okay, so 3 dimension meaning D is equal to 3. Where's my marker? So D is equal to 3. Ideal gas gas in 3 dimension with the energy momentum relation given as energy goes as P to the power S. Okay. The range of S for which the system may undergo a Bose-Einstein condensation at a non-zero temperature is. Okay. So again, you can use this relation that D by S should be greater than 1. Right. So D by S should be greater than 1. So what is this telling you? S should be less than D. Right. So in 3 dimension, that means your value should vary. Your S should vary from 1 to 1 or 2. It should be less than 3. Right. So S should take up this value. Right. So you can also look at, you or use this relation to correlate with what we have already known. So suppose if it is asked that in which dimensions DEC is possible for a massive boson and then for a massless boson. So how will you answer that, right? So you would say that for a massive boson, S is 2, right? According to this question, because epsilon energy is given as P square by 2m. So S is 2. For massive boson, S is 2. Okay. So for BC to occur, D, which is the number of dimensions, should be greater than S, right? So in that case, BEC is possible only in 3 dimension, not in 2D or 1D. Okay. But now if you take massless boson, your energy would be given as P into C. So in that case, S is 1, right? So for massless boson, S is 1. So that means BEC can occur when D is greater than S. So that means BEC can occur in 3 dimensions as well as in 2 dimensions. Okay. Not in 1 dimension, but in 2 dimension it's possible. So for massless bosons, you can get BEC in 2 dimensions, but you cannot get BEC with massive bosons in 2 dimensions. Okay. So that comes from the same relation that D by S should be greater than 1. So that's a very important relation. Okay. To remember. Okay. So I guess that's it. Thank you. And if there is any doubt regarding the questions that we have discussed or any conceptual doubts, feel free to ask me. Okay. I'll keep the thing on for some time because there's some time. So in case there's any doubt, anybody just say we can discuss. The most important part from this section is actually to get used to this concept. Okay. And these relations are very important. I mean, particularly the expression for the temperature TC, that is very important. The concept of how Bose-Einstein condensation starts happening as you go below the temperature TC, that concept is very important. Okay. So here you're saying that there's a normal phase and there's a condensed phase for T less than TC. So this idea, these concepts are important. And obviously one should remember or at least like get used to these expressions of the mean occupation number and this general expression so that you can work out for all different cases. Okay, so if you remember this, you can do it for Bose-Einstein, Fermi-Dirac, or classical, all of them. So be like well versed with these expressions. And this plot is very important also. This also tells you that how your chemical potential should always be lower than the ground state energy. That also comes up here. As you can see, there's nothing in this range for the Bose-Einstein case, right? So that's also an important point. N lambda cube defines the where quantum effects set in. This idea is important. Um, I guess the rest things will just follow up. Yeah, this question is actually quite standard question. So d by s should be greater than 1. So it tells you where Bose-Einstein condensation is possible, where it's not possible. Okay. So, yeah, these are some of the main things from today's discussion. So thank you. I'll just keep it on for some time in case there are some doubts. Okay, so I think let's call it a day. Thank you.